Let's go ahead and get started. We've got a lot of problems to try to get through tonight. So we'll go ahead and just get started right at time here at 8 o'clock. So same as usual, we'll just go through each of these one problem at a time. If there's one that you want to see, just say yes. If you don't want to see it, you can be quiet. Somebody else might want to see it. We do have some spots. There's quite a few empty chairs down here. If you guys don't want to sit way up in the back, we have quite a few down here if you want to sit in a chair. All right, so we'll just move right along here. Let's see. So number 1. Yes? Is that a yes? Yeah, okay, thanks. There's a lot of voices, so you guys pick up a little bit. So one significant difference between gases and liquids is that blank. And so if we look up down here, to look for a difference, gas is made up of molecules. Maybe true, gases can also just be atomic, but so can liquids, so it's not really a difference. The correct answer here is B. A gas always assumes the volume of its container. So if you have a gas in a container, it's always going to fill that container completely. If you have a gas in a 1 liter container, it's going to fill a 1 liter container. If you then transfer it to a 2 liter container, it's now going to fill a 2 liter container. Again, because gases, molecules travel in a straight line until they hit something, so they will eventually fill an entire container, whereas liquids don't. Your liquids can only fill as much as their volume is set. Right? So C, gases don't always have to be mixtures. D, gas may consist of both elements and compounds, and that's true, but so can liquids. So it's not a difference there. So the only answer there is B. Okay. All right. Number 2. Yes, sorry.
Could you possibly start with the test you worked your way at the beginning?
I'd rather not.
Okay.
Sorry. Just because the oldest stuff that we did was the first stuff covered, so I want to make sure we get to that. So number 2. We go to 2, it's just kind of a definition there. Number 3. Is that a yes? Yep. Okay, so number 3, sample of gas, 24.2 grams, initially at 4 atmospheres, was compressed from 8 liters to 2 liters at constant temperature. After the compression, the gas pressure was X number of atmospheres. And so in this case, we're given a little bit of extraneous data. We don't really care how much the gas weighs. It doesn't really matter. We don't know the identity of the gas, so we can't even find the number of moles. But we do know the pressure and the volume. And so for this one, we know that we have P1, V1 has got to be equal to P2, V2, and those always have to be equal to the same thing, so that's got to be a constant. And so I know that my P1 was 4 atmospheres, so we'll put that in there for P1, and V1 was 8 liters. So that's got to be equal to some pressure. I don't know P2, that's what I'm looking for, and I know that V2 is 2 liters. Okay, so when I just work that out, I get a P2 that ends up equal to 16.0 atmospheres. Okay, so just P1, V1 equals P2, V2 on that. It's the only data we're given, and we're told the temperature is held constant. And it looks like the amount of gas is also held constant, because we just have a sample of gas. Okay, let's see, number 4. Yes. So number 4, a balloon originally had a volume of 4.39 liters at 44 degrees Celsius and a pressure of 729 torr. The balloon must be cooled to X degrees Celsius in order to reduce its volume to 378 liters, or 3.78 liters at constant pressure. So the pressure is remaining the same. And so what we've got a case here is where we've got volume and, let's see what we're dealing with there, volume and temperature. And so for that, which one is this? 4. We know that V1 over T1 is equal to V2 over T2. And in this case, since we're just comparing the ratio, our pressure is okay to remain in millimeters of mercury or torr. We could also convert it into atmosphere to get the same answer here. The one thing we do need to make sure we do is convert our temperature into Kelvin. That's not an option. You always have to convert into Kelvin when you're using the gas laws. And so what we end up with is 4.39 liters over 317 Kelvin, and that's going to be equal to 3.78 liters over my T2 there. And so when you solve that for T2, you get 272.9 Kelvin, which is about 273 Kelvin, which is equal to 0 degrees Celsius. So you've got to subtract that 273 to go from Kelvin to Celsius. Okay, so just looking at all those different relationships that we learned about way back, first week in November there. Let's see. Number 5. Yes. So number 5, if 50.75 grams of a gas occupies 10 liters at SPP, then 129.3 grams of the gas will occupy X number of liters at SPP. Now, the kind of tricky one on this one is we're given these grams, but since the number of grams is the same, the ratio of the 2 grams would be equal to the ratio of the moles, because in order to convert to moles, we would just have to divide by the exact same value. So the ratio of the masses here is going to be exactly the same, so we don't really need to worry about converting this into moles, and we can't anyways because we don't have a molar mass. So in place of the number of moles, we can actually use the grams here, and we'll still get the same ratio. Even if we knew the molar mass and converted it into moles, we would still get the exact same answer. And so kind of what we're going to do here is we're going to use our equation where we've got P1 V1 over, and I'm just going to say M1 for mass, T1 is equal to P2 V2 M2 T2. Okay. Now we're told some things that's going to allow us to cancel some things out. We know that both samples, to start and to finish, are at STP. So that means the temperature and pressure on both of these is constant. So I can throw out temperature and pressure. So P1 and T1 are going to be the exact same as P2 and T2. So I can cancel them out on both sides of the equation before even putting numbers in. You can put numbers in too and just work it out. You'll still get the same answer. But now we can just go ahead and put these in. And so for V1, we've got 10 liters. And our mass is going to be 50.75 grams. So that's going to be equal to our V2 number of liters over 129.3 grams. And when you solve that for V2, you get 25.5 liters. And so really all that's doing is just setting up a ratio. If you have 50 grams of material, gas, and then you a little more than double that, well, that's going to a little more than double your volume as well. Okay? As long as it's the same gas, you're going to have the same effect on the molar. There are some seats at various places down here in front if you need a chair to sit in. All right. Number 6. Yeah, okay, so 6 is just applying ideal gas law here. Still on screen there. So for number 6, we know a volume at 60.82 liters. We know a temperature of 31 degrees Celsius, which is going to be 304 Kelvin. We know a pressure, which is 367, 7 millimeters of mercury. which is equal to 0.483 atmospheres. I just went ahead and converted that ahead of time. And what I'm looking for is amount of gas. So I'm looking for the number of moles. And so I know V, T, P, and N. We know R, of course, because that's a constant, 0.082058. That's liter atmosphere per Kelvin mole. Okay, so we know that we have PV is equal to nRT. So we know that N is equal to PV over RT. And when we plug in all those values, I'm not going to write it out here because it's easy enough for you to do on your own. We get an N of 1.177 or 1.18 moles. So that would be B for that one. Okay, so we substitute our value for pressure, volume, and temperature again. For this one, you do need to make sure that your pressure is in atmospheres and your temperature is in Kelvin. All right, that was 6. Number 7. Here we go to number 7. You want 7? Yeah. Okay. So for 7, what you're looking for is what affects those. There's two conditions given on both of those. You must say, what effects are those going to have on the volume? Okay, and that's the easiest way I always thought of doing that. So if you're just listening on the pencast, you can look at the options on here. So for A, so increasing the temperature, what will that do to the volume? Increase the temperature is going to lead to an increase in the volume. What about decreasing the pressure? Also leads to an increase in volume. So if you do both of those things, the volume is going to increase because they're both doing the same thing. For choice B, increase the temperature and keep the pressure constant. So if you increase the temperature, as we saw, that's going to make the volume go up. Keeping the pressure constant, well, that won't have any effect on the volume. And so if you do those two things, just the temperature increase alone will make that go up. Okay? Not as much as maybe what it would in A, but it's still going to make that volume go up. So we know what's going to happen there. For C, decreasing the temperature and increasing the pressure. Well, if increasing the temperature makes the volume go up, then decreasing the temperature must make the volume go down, and increasing the pressure also makes the volume go down. So if I both decrease the temperature and increase the pressure, both of those are going to make the volume go down, so the volume has to go down. Now the correct answer here is D. Okay, and the reason is because we don't know what's going to happen. We're going to increase the temperature. That's going to make the volume go up and increase the pressure. That makes the volume want to go down. So which one wins? Well, there's no way to know without knowing some values on it. So just by saying when you increase the temperature and increase the pressure, two things are going in opposite directions. So we don't know if it's going to increase, decrease, or maybe even stay the same with those two options there. And then the last one, keep temperature constant and decrease the pressure. Well, keeping the temperature constant has no effect on the volume. Decreasing the pressure would increase the volume, so that must be what happens. Okay. All right. Number 8. Yeah. Yes. So we have a density equation here. So the density of ammonia gas in a 4.32 liter container at 837 torr and 45 degrees Celsius is what grams per liter? So we want to set up our density equation here. Okay, so we know that we've got pressure times the molar mass is equal to the density times R times T. That was an equation that we learned in class. We know the pressure, so the pressure is equal to 837 torr which is equal to 1.10 atmospheres. We've got a temperature of 45 Celsius, which is equal to 318 Kelvin. What else do we know? We know a molar mass, since it's ammonia, so my formula is NH3, and so that has a molar mass of 17 grams per 1 mole, and we know our value for R. So all we're looking for now is the density, so we can plug everything in, and so we know the density is equal to pressure times molar mass over RT. So that's going to be 1.10 atmospheres, that's still on screen, times my molar mass at 17 grams per mole, all over my R, 0.08206. I'm just going to take that down to 06. And then my temperature is 318 Kelvin. And so when I work out all of that density, I get 0.717 grams per liter. Okay, the harder part of this one is just remembering that ammonia was NH3. That's something we would normally give you. But you definitely want to make sure that you kind of know some of the simpler molecules off the top of your head, like water. You know water is H2O. You should know methane is CH4. Ammonia is NH3. It's pretty much the three big ones that you should probably know. So you have to convert torr to atmospheres using 760 torr per 1 atmosphere. Okay. Yep. All right. Let's see, which one was that? Number 9. Yep. Okay, so for number 9, the volume of a sample of gas, 2.49 grams or 752 milliliters at 1.92 atmospheres and 60 degrees Celsius. The gas is what? There's some different ways of doing that. You can do this just using PV equals nRT, solving for the number of moles, and then use the grams over the moles, and you can get the molar mass. Or you can use the density equation that I just used, calculate the density since you know the mass and the volume here, and plug that into the density equation and solve for molar mass. They both give you the exact same answer. So I did it the second way, so we'll go ahead and look at that. And so, number 9, so we're given the mass and the volume. Now when we're looking for the volume or the density of a gas, in these problems, we want units of grams per liter so that our liters in our volume unit cancels with the liters in the R units. So we're going to go grams over liters. And so our grams here is 2.49. And then we're given 752 milliliters, which is 0.752 liters. And so we get a density of 3.31 grams per liter for our density. And now we can plug that into our pressure. Molar mass is equal to density times RT. We're looking for molar mass here. So that's going to be density times RT over pressure. And so now we know our density. It's 3.31 grams per liter times our R. Liter atmosphere per Kelvin mole times my T. Now my T was 62 degrees Celsius. We got to convert that to Kelvin. That's 325 Kelvin. And then all over our pressure, which was 1.98 atmospheres. And you can see the units are all going to cancel. My liters are going to cancel out, my atmospheres cancel, my kelvins cancel, and I'm left with grams over mole, which is good because I'm looking for a molar mass in grams per mole. So that's a good thing. And when we work out all of those numbers, we get a molar mass that's equal to 45.97 grams per mole. And then if we look at the different compounds that we've got to try out here, we've got NH3 that has a molar mass of 17, so that's not it. Neon has a molar mass of 20.2, and that's not it. NO2 has a molar mass of 46. Well, that's pretty dang close, and so that's going to be the answer there, C, NO2. SO3 comes out to be about 80, and SO2 comes out to be about 64. So C is by far the closest one. Questions at all on that one? Number 10. Yeah, 10 is kind of a hard one. So the volume of HCl gas required to react with excess magnesium metal to produce 6.82 liters of hydrogen gas at 2.19 atmospheres and 35 Celsius is blank number of liters. So the key with this one is getting a proper chemical reaction written out. So we're going to react HCl plus magnesium, and that's going to form hydrogen gas, H2, and if this were my problem, I probably would have gone ahead and said it creates magnesium chloride, just so you have that other substance on there if you couldn't figure that out. Now you've got to make sure that it's balanced, and we've got one HCl here, or one H here and two H's here. So the only thing I need to do to balance this is put that 2 in front of that HCl, and now it's actually completely balanced, which is kind of nice. Now, notice that everything here was a gas except for the magnesium. So the HCl and the H2 are both gases, and the conditions didn't change. So I'm at the same temperature, I'm at the same pressure, and so the only thing that can change really is the number of moles. And of course, if I change the number of moles, that's going to change my number of liters on there. So I see that I have a 2-to-1 ratio there of HCl to H2. So if I want to make 6.82 liters of H2, since my conditions are exactly the same, and I need twice as many moles of HCl, I'm going to need twice the volume to have twice the number of moles. And so it's just twice the 6.82. Okay, that's the short way of doing it. You can, if you want, go through, figure out how many moles of H2 gas that would be, calculate the number of HCl moles that would be using this stoichiometry, and then go back and use the ideal gas law to get volume, and you'll get the same answer. Either way works on that one. But it's a little bit of a shortcut if you recognize that all of the conditions are exactly the same, so the number of moles is just going to vary with the volume, or vice versa, I guess. Questions at all on that one? Let's see, number 11. Yes. So we've got a 12.2 liter vessel. It has 2.34 grams of carbon dioxide, 1.73 grams of sulfur dioxide, and 3.33 grams of argon, all at 42 degrees Celsius. And we want to know what is the pressure inside of that one, okay, in millimeters of mercury. So what we need to know, really at this one, we know the volume and we know the temperature, and we're looking for the pressure. So what we need to know is how many moles of material do we have in there. We're given grams. So what we've got to do is convert all of our grams into moles there. And so for CO2, so for our number of moles of CO2, that's going to be equal to 2.34 grams over 44 grams per mole. So that's going to give us 0.0532 moles of CO2. My number of moles of SO2 is going to be 1.73 grams over 64 grams per mole.
And that comes out to be 0.027 moles. And then the number of moles argon is going to be 3.33 grams over 39.95 grams per mole. And we get 0.0833 moles. So my total number of moles now is equal to 0.164 moles. And so now we can plug in our values for PV is equal to nRT. We're looking for pressure, so we know pressure is equal to nRT over V. I'm not going to go through this whole one just because it takes time. You should be able to do this. That was the hardest part on here. We know our number of moles. We just calculated it. R is a constant. Our T, we just need to convert from Celsius to Kelvin by what was given in the problem. And then our V is the 12.2 liters. And we calculate all of that out. You're going to get an atmosphere pressure. It asks for it in millimeters of mercury. So you just got to remember there's 760 millimeters of mercury or 760 torr per atmosphere, and then you just convert back into that unit. Okay? So you should get B for that, 263. But this is kind of the hardest part here, is getting all those moles. Let's see, number 12. Yep. So in the gas mixture of helium, neon, and argon with a total pressure of 8.4 atmospheres, the mole fraction of argon is what? If the partial pressures of helium and neon are 1.5 and 2 atmospheres respectively. So we know the pressures of helium and neon. What we don't know is what's the partial pressure of argon. However, since the sum of all the partial pressures have to add up to the total pressure, we can just find it by subtraction. Okay, so I know that my P total is equal to pressure of argon plus pressure of neon plus partial pressure of helium. And so we get 8.4 atmospheres is equal to my partial pressure of argon plus, let's see, neon is 2 atmospheres plus 2.0 plus pressure of helium at 1.5. And so my partial pressure of argon is going to be equal to 4.90 ATM. Okay, so now I know my partial pressure of argon, and now I can find my mole fraction, because the mole fraction of argon is going to be equal to the partial pressure of argon over the total pressure. Okay, so that means I'm going to have 4.90 ATM over 8.40 ATM, and that comes out to be 0.583. That's the nice thing about the ideal gas law, is the identity of the gas doesn't matter. All gases exert the same amount of pressure based on the number of moles. All right. Let's see. Number 13. Just kind of a definition one. That was kind of weird. The answer is A. B says that the collisions between gas particles are inelastic, and if they were inelastic, that would mean that they lose energy every time they collide. Well, if that happened, all the gases would very rapidly turn into liquids, and we'd have no gases to breathe. Everything would be very different. So that's one. Average kinetic energy of the particles of a gas is directly proportional to the centigrade temperature. Not centigrade temperature, because what would happen for a temperature of 0? And that would mean we have no kinetic energy. That doesn't make sense either. So it is directly proportional to the Kelvin temperature. And then attractive and repulsive forces between gas particles are stronger than those tiny particles in constant random motion. I don't really like the term random motion on that one, but that is the right answer. All right, 14. Yes? Okay, so the following gases, which of these will have the greatest rate of diffusion at a given temperature? So remember, your rate of diffusion is dependent on the inverse of the molar mass. So in other words, the smaller the molar mass, the faster it will diffuse because it's trying to get through a tiny hole. Think of gases trying to escape a balloon. So the smaller the gas, the easier it is for it to get out of that hole. And so we're looking for the smallest molar mass on these. And so HCl is 36 grams per mole. NH3 is 17 grams per mole. That's pretty tiny. CH4 is 16 grams per mole. That's a little bit smaller, so that's our winner so far. Argon is 40, and HBr is 81. And so the winner that will diffuse fastest is CH4 at 16 because it has the smallest molar mass. Okay? We don't need to calculate anything there because we just have a proportionality for a fusion. We don't really have an equation. Right? So the answer is going to be the one with the smallest molar mass. If we were looking for the lowest rate of diffusion, then we'd look for the highest molar mass. All right. Number 15. Yep. So a tank containing both HF and HBr gases develop to leak. The ratio of the rate of diffusion of HF to the rate of diffusion of HBr is what? Okay. This is 15. So we can say that we have rate. We're looking for the rate of HF over rate of HBr. Okay, and so that's going to be equal to 1 over HF over 1 over HBr. That's molar mass of those two. Okay, so that simplifies a little bit to the square root of molar mass of HBr per or over molar mass of HF. So that's going to be square root of 80.9 over basically 20. And that comes out to be 2.01. And so that's the answer there is B. So HF will diffuse twice as fast as the HBr. So the tank will lose HF twice as fast as HBr. That's about all you can really say. We don't know how fast that's going to be. It's just going to be twice as fast. All right. Questions on that one at all? It's kind of a weird concept there. 16. Yeah, so arrange the following gases in order of increasing average molecular speed. So we're at a single temperature, 25 degrees Celsius. Okay, so there's a certain amount of kinetic energy. Okay, the average kinetic energy is determined strictly by the temperature. And since kinetic energy is equal to mv squared, then the smaller the mass, the higher the velocity. So that's what we're looking for here, really, to help rank these. The smaller the molar mass, the faster the velocity is going to be. So if we look at the molar masses, we've got helium at 4, oxygen at 32, CO2 at 44, and nitrogen at 28. And so we want to go in order of increasing average speed. So we want to put the slowest one first and the fastest one last. And so the slowest one is going to be the heaviest one. So that was CO2 at 44. And then next was O2 at 32 grams per mole. N2 at 28 grams per mole. And then helium at 4 grams per mole. So that's the fastest one. So that's why the answer for that one is A. It's all about molar mass for that one. Number 17. Kind of remembering what we said about an ideal gas. And one of the things is that they have no attraction for each other. They don't occupy any volume, and they have no attraction for each other. 18, that's the definition of a joule. We would give you something like that on the test. That was just to have you look something up. I guess you got to remember the joule itself is a compilation of units, kilogram per meter times meter squared per second squared. And so there are times when we need to go in and use that definition for a joule in order to get certain units to cancel out. And we'll see, I think, a little later in the semester, or maybe early next semester, where we actually have to use the kilogram. We have to use a kilogram per mole in molar mass in order to get things to work out properly. Let's see, number 19. Easiest way to know if something's a state function, it's capitalized. Non-state functions are lowercase, state functions are uppercase. I didn't know that until I was teaching chemistry. Nobody ever told me that when I was a student. Would have made life a lot easier. Or if they did tell me, I didn't listen. That's probably the case. Let's see, number 20. Yes. So we want to know what is expected. So this is a kind of a thought problem. What is expected when the combustion reaction shown below takes place in a thermally insulated container outfitted with a movable piston at constant atmospheric pressure? So what that means is that temperature is going to, no heat is going to be lost by that system. It's all going to be absorbed there. And the piston can move against a constant pressure. If the volume needs to expand, it's going to do that so the pressure remains constant. And we're told that, kind of an important clue here, we're told that it's a combustion reaction. Well, if you're combusting something, what is it doing? It's exploding, it's catching on fire. There's heat involved, there's fire and all that kind of stuff. So, if we have a volume of gas and we basically burn it, make it explode, we have a lot of heat coming out. So now the gas inside in that chamber is going to get hot. And what do hot gases do? They expand. Okay, so it's going to expand. Now, if that piston were fixed and the volume couldn't change, then the pressure would just go up. But we've gone the opposite way here. The pressure is going to be the same, so the volume can expand. So that piston is going to go up. And so that piston goes up, that increases the volume of the space where the piston is, so the volume is going to increase. And since the system is pushing that piston out against the atmosphere, then it is doing work. So there is work being done by the system. Okay, since that system is expanding into the surroundings, the system itself is doing the work. It's kind of a weird one to think about. Okay. But you had to realize that combustion reaction, what was going on, was burning, exploding, however you want to think of that, and it's kind of where it starts at now. All right, 21. Yeah. Yeah, last one. So the question is, what's the difference between work being done by the system and work being done on the system? So if you're doing work on the system, it means that so that would be like pushing that piston down, so forcing that system in a way it doesn't want to go, as opposed to the system expanding against the surroundings. That would be kind of the difference there. Does that make sense? All right. Let's see here. So 21. We've been pretty good on some of those definitions there. 22. Good. 23. Yes. So 23, we're given a reaction and we're given a delta H. Now we see that delta H has a negative value, and that means that it's what? Exothermic. It means that it is losing heat. So heat is going out of that system. So exothermic. And so heat is then being released by the system. Okay, exothermic, an exothermic reaction would feel hot to you because it would be releasing energy into you, your part of the surroundings. So it would feel hot. So that's going to be exothermic. So exothermic releases energy, endothermic absorbs energy. And exothermic has a negative delta H, endothermic has a positive delta H. Let's see, number 24. Yes. So the value of delta H for the reaction below is negative 126 kilojoules. How much heat in kilojoules is released when 2 moles of NaOH is formed in the reaction? Okay, well, I'll work this one out. It might be easier for you to see. So I know that I get negative 126 kilojoules per 4 moles of NaOH formed. So I get how many kilojoules per 2 moles of NaOH formed? Okay, so if I make half as much material, I must have released only half as much heat. And so the answer for that would be, so the delta H would be negative 63 kilojoules. Now you'll notice that negative 63 is not an answer there. Okay? And that's because of the wording in the problem. It says how much heat is released. So the sign there just tells me which direction the energy is flowing. Okay, so my delta H for 2 moles would be negative 63. But I could also say that 63 kilojoules are released. Okay, there's no such thing as really negative energy. It's just energy flowing in or out, and the sign tells us which way that energy is flowing. It's a lot like money. Okay, so like if you're paying $10, you have a minus $10 flow, and the store has a plus $10 flow. You didn't lose negative $10, you lost $10, and they gained $10. The amount of dollars is always positive. The sign just says which way it's flowing. Does that make sense? Hopefully? So since it's energy, it's asking for the amount of energy released. That tells us already that the negative sign is taken care of. We know which way the energy is flowing. It's just looking for the value of how much energy was flowed. All right. Number 25. Yes. Okay. 25 is a very similar problem to the one I just did. Okay, so we've got the value of delta H for the reaction below is negative 336 kilojoules. Calculated heat in kilojoules released to the surroundings when 23 grams of HCl is formed. Okay, so if we look at the reaction, I know that I get negative 336 kilojoules per 3 moles of HCl. Now, I can just multiply that by the number of moles of HCl that I made, and moles of HCl cancel and leave me with kilojoules. The problem is, it didn't give me moles of HCl, it just gave me grams of HCl. So I've got to convert my grams of HCl to moles of HCl. So we'll do that. So I have 23.0 grams of HCl times 1 mole per 36.45 grams. And I get 0.631 moles of HCl. So now I can take this and put that up here times 0.631 moles of HCl, and you get a negative 70.7 kilojoules for the delta H for that amount. But again, it uses the word how much energy is released for that. And so that takes care of the sign. And so the answer would just be 70.7 kilojoules. Okay. So it's all just looking at how much does the reaction say was used and how much did you actually use. Just becomes a stoichiometry problem. Heat follows stoichiometry as well. So we have a sample of aluminum absorbing 9.86 joules of heat. Upon which the temperature of the sample increases from 23.2 to 30.5 degrees Celsius. Since the specific heat capacity of aluminum is 0.9 joules per gram degree Kelvin, the mass of the sample is how many grams? Okay. Okay, so we know that we have heat is equal to m times c times delta T. We know the heat, we know the specific heat, and we can find the delta T because we know the starting and finishing temperatures. So we just need to solve for the mass. So that gives us 9.86 joules is equal to our mass times our specific heat, 0.90 joules gram degree Kelvin, not degree Kelvin, just Kelvin. There's no degree there. Times our delta T, which is 30.5 minus 23.2. So we get 7.3 Kelvin. So our Kelvin temperatures are going to cancel. And it doesn't matter if you use Kelvin or degree when you're looking for or Celsius if you're looking for a change, because they're the same sized unit. They're just shifted in their scale. So the change in temperature, if it's 7.3 degrees Celsius, it's also 7.3 Kelvin for a delta T. Okay, my joules are going to cancel here, and so we can now just solve for a mass, and we get 1.50 grams. Pretty good now? Okay, so that was 26. How about 27? So 27 is very much the same kind of problem. We're just solving for a different variable there. We still want to use heat is equal to mass times specific heat times our delta T. Okay, we know our heat, it's 29.0 joules. We know our mass, it's 15 grams. We don't know our specific heat capacity, we're looking for that. And our delta T there is going to be 15 Kelvin. And so when we divide all that out to solve for C, we get a value of 0.128 joules per gram Kelvin, or 0.13 to 2 sig figs. Are we good now? Let's see, 28. Yes. So for 28, we're given a reaction we want to try to get, and we're given two reactions to try to manipulate in order to get that third reaction. And so the two reactions that we're given, we have IF, I'm going to leave off the phases because they don't really matter here, plus F2 goes to IF3 that has a delta H negative 390 kilojoules. And we've got IF plus 2F2 goes to IF5, and that has a delta H of negative 745 kilojoules. Okay, now we're trying to get to IF5 goes to IF3 plus F2. Okay, so notice in the reaction I'm trying to get to, IF5 is a reactant. The two reactions that they gave me, only that second one has IF5 in it, and it has it as a product. So what do I need to do to that reaction? I just need to flip it. And I don't need to multiply it by anything because I'm just looking for one IF5. Okay, now if I flip that reaction, what do I need to do to the delta H? I need to change its sign. Okay, so I'm going to cross this one out so we don't confuse ourselves, and I'm going to flip this one. So now I've got IF5 goes to IF plus F2 with a delta H of positive 745. And now if we add this first reaction and that third reaction together, our F2s here cancel, our IFs cancel. Oh, that's a 2F2. So one of those F2s cancel. The 2 cancels out, and I'm left with still an F2. There we go. And so what I end up with is IF5 on the left goes to IF3 plus F2, which is exactly what it was asking for. And when I add the delta H's together, I have negative 390 plus 745, and I get a positive 355 kilojoules. Any questions on that one? Okay, how about 29? So I'm not going to go through 29 because it's actually the exact same thing. If you look at it, I've got to get those 2 NOs on that second reaction over into the product side. I'm starting in the reactant side. So the only thing I need to do is flip that second reaction, change the sign of its delta H, and just add those 2 reactions together. And you should get C for an answer. How about number 30? Okay, 30, I have 2 people coming asking me today. So this one, you've got to remember what a formation reaction is. A heat of formation comes from a formation reaction. We have a very definite definition of what a formation reaction is. So a formation reaction is a reaction that creates 1 mole of a product from its elements in their standard state at room temperature and pressure. Okay? So we can throw B out pretty quick because it's making 2 moles of a product. You can only make 1 mole of a product for a formation reaction. That's why we can do that for. If we look at A, it's got 4H gas. Well, what's the elemental state of H? H2. So that throws that one out. We've already thrown B out. For C, 12 carbon, that looks okay, although it says it's a gas. What's the elemental form of carbon? Graphite. Okay, carbon and graphite. Carbon does not exist as a gas at room temperature and pressure. Otherwise, you wouldn't have pencil that made out of graphite. The H2, even if you forgot about carbon, or if you thought the G stood for graphite there, it's got 11 O's. Well, does oxygen exist as O or O2? It exists as O2. So O is not the standard state for oxygen, so that one's got to go. D is the correct answer. It's got nitrogen as N2, which it exists as. It's got oxygen as O2, and it makes 1 mole of NO2. So that's 1 mole of a product made from elements in their standard state. So that's why that's a formation reaction. And then E's problem is the hydrogen, because that should be H2, not just H. Okay? All right. Let's see, 31. Yes. So the following is that delta heat of formation is not 0 for which? And so remember your delta H formations is always 0 for any element in their standard state. Okay, so we've got to look to see what's the standard state. Carbon in graphite form, that is the standard state for carbon, so that's going to have a delta HF of 0. N2 gas, nitrogen exists as a gas under standard conditions. So that's going to be 0. O2 gas, standard conditions, so that's standard state under standard conditions. F2 solid. What's F2 under standard conditions? It's a gas. Okay, it's just like chlorine. It's actually lighter than chlorine. So it is a gas. And then chlorine is also a gas. So the answer there is F2 solid. F2 is not normally a solid, it is a gas under standard conditions. Let's see. 32. Yes. So we're given the delta H reaction. We're trying to find the delta H reaction here, given the delta HX for some of those various components there. Okay, so remember for delta HF, or a delta H reaction rather, is going to be the sum of our delta H's for our reactants minus the sum of the delta HFs for our products. Okay, and we've got to remember to multiply the delta H's by any balancing coefficients. Okay, so my delta H reaction here is going to be the calcium salt there with the arsenic, and it's going to be negative 2346.0 plus 2 waters there, so that's going to be 2 times negative 285.9. So there's my products minus my reactants, and so my reactants are going to be negative 986.6 plus 2 times my other guy there. It's getting hard for me to write down there. Okay, so when you sum all of that up, you get negative 130.4 kilojoules. I left off kilojoules when I was writing to save space. I wouldn't have made it to the end of the line. Okay, so when you're using delta H's, it's products minus reactants. Okay, 33. Yeah? No? Okay. Yeah, okay. So 33 is pretty much the same kind of problem on that one. The main difference is that we are missing one of the components, but we know the delta H of the reaction. Okay, so we can still say that the delta H is going to be equal to the sum delta H of my products minus some delta H of reactants. And here I know my delta H, it's a positive 177.8, so that's got to be equal to the sum of my reactants there, or my products rather, negative 393.7 plus the delta H for the CaO, which I'm looking for because I don't know that, minus negative 1207. That's all I have for my reactants there. And so when I work that out and solve for that delta H as CaO, I get negative 635.5 kilojoules. Okay, so again, it's a little bit different for that problem because normally we're used to solving for the heat reaction, but here we are given the heat reaction. We just had to find the delta H for one of those products. Okay, number 34. Yes. So we got to use the average table of average bond energies below and find the delta H for the reaction. Now, when you're using bond energies, this is when you have to do reactants minus products. Okay, the sum of bonds broken minus sum of bonds formed. Okay, so it's backwards from any of the other stuff. This is the only one that goes this way. So we can just break all of the different bonds. We want to go sum bonds broken minus sum bonds formed. Now, for those of you, I know some of you are just getting ready to head out. I noticed this morning we didn't have any practice problems on Redox, and Redox is on this exam. So there are some Redox problems up on D2L now for Redox. It's only like 4 problems. Okay, but they are in a separate file. I'll go through them tonight with you guys as well. So this isn't actually the last problem. So for this one, we want to take a look at what's broken. So we're going to break 2 carbon-hydrogen bonds, 1 carbon-carbon triple bond, and 2 hydrogen-iodine single bonds. So that's going to be 2 times 413, 839, and 2 times 299. When I add all of that up there, I get 2263. Okay, so that's how many kilojoules it takes to break all of those bonds. And now for the bonds formed, I've got 4 carbon-hydrogen bonds, so that's 4 times 413. I've got 1 carbon-carbon single bond, so that's 348. And I've got 2 carbon-iodine single bonds, so that's 2 times 240. And so that all adds up to 2480. And so you end up with a negative 217 kilojoules. So the answer there would be E. Questions on that one at all? You want to make sure that you don't flip-flop that one. All right, let's take a look at some of these redox ones. I'll put them up here. So that first one, it says, which atom in the compound K2C2O4 has a positive oxidation state? So we've got to go through the oxidation state rules. And you want to remember that those rules are not on the equation sheet. They're not on the constant sheet. So you got to know those. Put them on your card if you don't remember how to use them. So we just go through our set of rules. Do we have anything in elemental state? No, because we have just one compound. Do we have any oxygens? We do. They get a -2. I just do my total accounting down below, so I get a -8 there. Do we have any hydrogens in the compound? No. Do we have any group 1As? Yes, we do. We've got potassium here. They get a +1. There's 2 of them, so I'm just going to keep my accounting down there at a +2. We don't have any group 2As. We don't have any monatomic ions. So now we know that the sum of all the oxidation states have to add up to the overall charge, in this case 0. So what do I need to add to a +2 and a -8 to get to 0? A +6. So I know that the carbons total a +6. There's 2 carbons, so each of them must have a +3. And so when we look at the answers here, it says which has a positive oxidation state. The answer would be B, both potassium and carbon. Okay? The second problem here, it says, which of the following is true for the following reaction? So our reaction is Cu plus ZnCl2 goes to CuCl2 plus zinc. So what it's asking for is what's oxidized, what's reduced, what's an agent, all that stuff. So we want to assign oxidation states. We go through the rules. I'm just going to do this kind of quick. Our elements here are going to get zeros. We go through all the rules and nothing happens because there's nothing else in here. So we got to use that one rule at the very bottom that says if you have a compound and you haven't assigned a halogen, give it a -1. So that chlorine's now is going to get a -1. And it gives it a total of -2. Same over here. And so now that allows us to give our zinc here a +2 and our copper here a +2. Okay, so now we look to see what changed, and I see that my copper went from a 0 to a +2, and my zinc went from a +2 to a 0. Okay, so if we look here, so is copper serving as a reducing agent? Our reducing agent is the thing that was what? Reduced or oxidized? Oxidized. Remember, your agents are opposite of what happened to it. The agent is what it did to something else, and the opposite happened to it. Okay, so was copper oxidized? The answer is yes. Copper lost 2 electrons, so it was oxidized. So it is a reducing agent. We want to look at the rest of these. B is copper is oxidized. Well, that's true too. C says zinc 2 plus is reduced. So our zinc 2 plus here went to a zinc 0, so it did get reduced. It gained electrons. So on this one, all of the above statements are correct. You can see I got fooled on this one too because I was trying to rush it right before coming down here. Okay, so all of those are correct. Okay. I'm not going to do 3. 3 is messy. You could do that one on your own. And then number 4, I want to teach you a little bit of a trick on that one. So number 4, you could go through each one of those and assign oxidation states to everything and just see if the oxidation states change. That'll give you the right answer. Got a little bit quicker way for you. If you look at the reactants, see if you have anything in an elemental state. If it went from an elemental state into a compound, then it got oxidized or reduced. If it went from a compound into an elemental state, it's almost certainly got oxidized or reduced. Okay? And you're going to have a redox reaction. So it says which of them is not a redox reaction. If we look at A, we look at magnesium. It's magnesium by itself, elemental in the reactants. It's part of magnesium chloride in the products. It got oxidized. Okay? We look at B, so that's a redox reaction. We look at B, we've got elemental oxygen in the reactants, and then the oxygen is part of a compound in the products. It actually got reduced. We don't care if it got oxidized or reduced, but something happened to it, and so that's a redox reaction. We look at D, we've got sodium, elemental state. It's part of a compound in the product. Or we have H, part of a compound, and then it became elemental in the product. We definitely had a redox take place there. The only one where that doesn't hold true is C. Everything is in compounds there. It's also a compound in the end. It doesn't mean it's not a redox reaction, so you should check it. But if it's elemental going into a compound, it's almost certainly a redox reaction. All right, I've got that sheet up on D2L, so you can take a look at it with its answers. I will get this posted as soon as I can. Best of luck to you tomorrow, folks. I'll be in my office off and on, so if you need some help, check in. Don't forget to finish your homework tonight.